Welcome to the second edition of our brand new event, Robolunch. I hope you can hear me good. My name is Etienne Axmann. I work in the VDMA, and there I am responsible for a sector group called Integrated Assembly Solutions. And feel free to enjoy our lunch, and we will garnish it with three fascinating stories. This time, we would show you innovative types of gripping. So, each presentation will be 8 minutes long, followed by 4 minutes of Q&As. Please ask your question in the meeting chat, and your microphones and your cameras are switched off by default settings. Please note that the VDMA compliance rules apply, and that we will record this event here. Our program today features input from InnoSize, No Touch Robotics, and Visevi. And the slogan is "Get a Grip." And we will see in the next minutes bio-inspired handling systems, ultrasound waves generated pressure fields, and camera-based gripping systems. And let's not lose time and go straight to our first speaker, Marc Schöneich. He is CEO of InnoSize. Marc, the stage is yours. Please introduce yourself. I give you the presentation rights now. So now it should work.
Perfect. I just select the right screen. Here you go. Normally you should see the presentation. Perfect. Short introduction. My name is Marc Schöneich, CEO and founder of InnoSize, and I'm quite happy to join my lunch with you today, and with a really nice topic, of course, gripping without some stuff and gripping with new stuff. So I thought about, when you speak about food like cheese, the new cheese is without any gluteins, and it's without any palm oil, and it's without milk. So why gripping without any energy and stuff like this? So but of course with new features. I'm quite happy to share some insights with you today. Speaking about InnoSize, so we have gripping without any energy, and we turn robots into geckos. And when I'm eating stuff, normally for lunch, I like to watch videos or some other, or reading mails probably sometimes. I just want to share a video, what we are doing, to give you an insight what's happening at InnoSize. I hope this is working. I try to put the music behind. Let's just give me a mark if this is working. Okay, here you go.
We live in a world of materials. These materials appear in different forms, sizes, and shapes. At InnoSize, we take on the challenge of handling the most sensitive, tiny, or demanding components. We develop gripping solutions to automate currently impossible or cost-intensive processes. More than 10 years of research at INM, Leibniz Institute for New Materials, built the foundation for Geccomere, a bio-inspired technology based on the function of gecko toes. Blending science and engineering, we move parts below 10 microns, pushing the limits of microassembly. Fast, precise, and sustainable. What applies to our team also applies to our technology. Take a closer look. Our customers save valuable resources and costs as our grippers perform without external energy. We partner with well-known companies to combine innovative technologies with the highest industrial standards. This synergy brings a disruptive change to the handling of sensitive components. Easily adapted to different systems, the technology makes a key contribution to ecological, social, and economic progress. Once installed, the lightweight gripper operates noise-free, improving working conditions for collaborators. The structure increases quality and reduces scrap rate, as the flexible pillars do not leave any scratches or residues. our specialists push the boundaries to best meet the market's needs. Based on physical van der Waals forces, attachment and detachment does not involve magnetism, chemical glue, or suction. The bio-inspired material paves the way for pick-and-place applications under extreme conditions, such as high temperatures or even vacuum. Innersize is the next step towards sustainable production.
So gripping without any energy, how does it work? You'll see it in the video a little bit. So we can, at Innersize, we are not building robots. We are not building grippers. We are building the fingertips of robots with grippers. So pick and place for us is working by microstructured polymers. So we are expert in polymer technology and microstructures to create this adhesion force by using van der Waals interactions with about 1 kilogram per square centimeter, and we detach it like a second. We can detach it like with a quite easy detachment mechanism, like the Gecko is doing this as well. I already showed this slide at the VDMA Maschinenbau-Gipfel in Berlin. So my motivation, what we are doing is, well, of course we can like reduce suction grippers and stuff like this. But when we look at this, like this modern production site for batteries, for example, our motivation is to rule out the entire blue cables here. So everything which is suction cups, stuff like this is quite important for us to say, okay, for a sustainable future regarding machine building and gripping, of course. And as well at the same time to challenge new environments for gripping, like automation opportunities in clean rooms or vacuum production as well. This is working from really small parts to square meters. So I don't want to bother you with some sales slides. So we have just a nice slide where you see some pictures, but generally it's about cobots, of course, which we can equip with our technology. You see here, production automation. We have a standard product which is sold by Schunk, so we have a really good partner regarding applications here for a standard product. So of course, this is called Schunk Ateso. We won some prizes, of course, as well as German Innovation Award. What is kind of interesting here on this side, we speak about micro assembly. So the smallest gripper which we built is like 10 times smaller than a human hair. Yeah, so for a new miniaturization applications, this is quite interesting. As well for a new LED pick and place options. I prefer to share 3 application cases with you, where we have really used our technology to push boundaries in the production. So we have here on this side, we see the fuel cell assembly, where we use a gripper just to handle parts, which are where we need the gripper which is residual free, which is really handling fragile surface with a high cycle time at the end of the day. In the middle here, you can see a device which is coming from packaging. So where we see that this is from Schubert. So this is not a secret to speak about this here. So we see that we have here equipped the system with our grippers. So avoiding blue cables, as I already mentioned at the beginning, which is leading to a tremendous cost savings as well as CO2 footprint reduction. And here, normally there should be a small video. Yeah, you can see it's the handling of small parts, glass fibers for the manufacturing of quantum computers in the future. This is something where we are really deep inside as well, already to handle this kind of parts, micro lenses, micro optics. Really interesting as well for this technology. And this is already. So I prefer to have some chat or some questions. So you see our team for machine engineering. It's quite diverse. So nearly 50% women, and we are always looking, of course, for new employees. So we are now 2 years old, more than 20 employees, and growing every day. We are looking not for money. We are looking for customers. This is something new for startups, and of course integration, cooperation. But as well, this is the most important thing here in this round to speak about partners which have the same vision about CO2 neutral production, about microstructures, microtechnology, but as well AI. And I hope to learn something as well from the next talks, how to integrate, for example, camera vision in our systems. Thank you very much.
Yeah, thank you, Mark. it was a little bit quiet, this presentation, but maybe you can share the video afterwards, if it's possible.
Yeah, I will share. Yeah, it was quite new to try this platform. But I will send a link in the chat to look at the video once again.
Okay, thank you. Yeah, we are now ready for your questions. Yeah, let me see in the chat if there are any questions for you.
I tried to increase the volume, Patrick, but it was I didn't know what to do, how to improve it.
So, at the moment there are no questions, but I have one question for you. Are there any clue residents on the surface from this gripping workpiece, or?
Yeah, they are generally say there are two hearts in my chest, as to say. So when I speak about as a sales and compared to other grippers, there are no residues. So imagine when you have getting a new windshield for your car, you see this round residues from suction grippers or something like this. So this is
okay.
Nothing which we have. But of course, when you go in contact with the surface as a material scientist and engineer, of course, there are, when you go into contact with a surface, there are always residues, but we speak about residues which are so small. We have qualified even for display and SMD applications in semiconductor industry. So this is not a lot, but of course there are some polymer chains which are running over the surface when you get in contact with something. Yes.
There is one question, Jetson. What is the highest weight that you can grip with the gecko gripper approach?
Generally, so we can handle 1 kilogram per square centimeter when we speak about a smooth surface like glass. The heaviest part which we are currently handling are window sheets for trains. They are about 140 kilograms, but at the end of the day, you just need a bigger gripper. So when you imagine you have like a really heavy part, you just add several stations or several points. You add a gripper, and you just calculate the surface you need, and it's working. So this is this is not a problem. It's more about which surface to use and which force to get there. Yeah.
Okay.
But
last question is, how do you release the workpieces?
Yeah, I try to explain a little bit. Of course, 8 minutes, including the video, was a little bit challenging. You can release it really like a gecko is doing it. So you press it a little bit harder. These hairs are getting tilted. We call this buckling, and you can release the part. So this is how nature does it. But at the end of the day, you can just turn the part a little bit, or you can turn the robot head, or you can tilt it a little bit, or it's really depending on. You can even spread. So you can imagine to have a release mechanism where you have two different half sides which are opening like a little bit, or you can use completely out of scope things like ultrasonic waves and stuff like this.
Okay, good. Thank you very much. Let's give Mark a virtual applause.
It wasn't a real, it was a real applause. Thank you. Thanks.
Okay. Yeah. Let's move on the second speaker. Welcome Marcel Schuck. He is CEO of No-Touch Robotics, and yeah, the stage is yours. Marcel, please introduce yourself. And yeah.
Thank you, Diane, for the kind introduction. I hope you can all hear me. Can you give me the option to share my screen here?
Yes. 1 second. So now it should work.
Yes, perfect. So you should be able to see my screen, right?
Yes.
Yes, perfect. So perfect. So welcome also from my side. My name is Marcel, as already introduced, CEO and co-founder of No-Touch Robotics. We're based in Zurich, and No-Touch Robotics is a spin-off of ETH Zurich. We were incorporated mid of last year, and our technology that we are commercializing here is based on 5 years plus of research. I think the usual university spin-off path here. And as of July this year, we are about 8 full-time equivalents and growing. And as mentioned, we're a spin-off of ETH Zurich. So to start with here and to give a short introduction of what we're doing and why we are here today for this lunch meeting is if you look at the evolution in robotics that has taken place since the 1990s, you can see this really drastic shift from robots being low versatility, very high priced, having to work in non-collaborative environments, to robots that are capable of being used on a desktop, being used collaboratively and massively going down in price, and being highly adaptable to various use cases. However, if we look at what is on the front of the robot, so the end effector, the gripper, we can see that there has been some evolution, of course, but in the end, leaving out these highly innovative solutions down here, most of the robotic grippers rely on the fact that I need to generate a clamping force or a gripping force between a gripper and an object. And for very, very small components, oftentimes the issue is that because in such a gripper I can only use parts of the object surface, even if I embrace them, that I have high local forces and then either gripping traces or residue that accumulates on the surface. And so we have started out to create, or in an attempt to create a solution for this. So our core technology is not touched part at all. So you can see one of our earlier demo systems here. We have a robotic arm, and then this gripper here in the front that looks like 2 half sphere caps, and they generate an acoustic field in which then the object is trapped in the middle of this acoustic field and is completely levitating without any mechanical contact. And the way this works, or the way that such a system works, basically follows more or less always the same patterns. So what you can see is we generate sort of an acoustic hologram here, and the shape and distribution of this acoustic field, and thereby the shape and distribution of the forces we can generate and adjust to the specific use case. And we do this by having a system that consists of some controls, FPGA-based, power electronics, and then an array of ultrasonic transducers. And with this, we synthesize the field to the needs that we need. And we can not only do this in a static manner, but we can also do this dynamically. And this works for gripping applications mostly in air, but it also works in other media such as water, or we have a few use cases where we even handle single cells in suspension. And to give you an overview here, so the forces that we can generate with this technology are in the range from micronewtons to millinewtons. So this is something for very small, very fragile objects. So not for big parts, but rather for small parts. Similar to Mark, to give you a brief overview of what are our areas of activity. So most of our use cases that we serve with this technology are about cases where the individual part is of really high value. And this mainly in 4 areas. Optics is a big part for us. Then microscopy, this is where we even handle single cells. Micromanufacturing and semiconductor handling. And size-wise, this ranges from around 10 micrometers in cells. Cells in the human body are usually between 20 and 100 micrometers. And then here, 2 parts that are up to 10 millimeters in size. And you see an example here in this picture of a watch dial. Of course, Swiss company has to do something with watches, where you can see how numbers that are ultra highly polished are placed on the face of a watch. Here I've prepared a short video. I hope that it works. So what you can see here is a pick and place operation with a small watch part again. So what you can see here is that the gripper approaches this grid structure. This is an acoustically transparent surface. The acoustic field is activated. By this, the part is then picked up. And if we want to place this part again there, we just do the same thing in reverse. Earlier, I promised you that we can also do dynamic fields, a video regarding this here. This is a very simple demonstration just with a piece of styrofoam, but you can imagine other particles here. So what you see is we levitate the part in the acoustic field, and then we adjust the position of the pressure distribution in this acoustic field such that this object is translated horizontally and also vertically. And we also have systems where we then can even control the rotation. As there is no mechanical contact between the object and the gripper, we can of course also do this for liquids. You can see this in this video here. So you see a small liquid droplet being levitated, and this is one of the cases where you see then a camera looking at the object, and we can then do closed loop control of the position. We can dampen the vibrations. We have a lot of possibilities in assembly and control of this object. And because I often get the question, how stable is this whole thing? How high are the forces that we can adjust with this? So just recently, back in October, we had our technology launched in a CubeSat. So what you can see here is this CubeSat assembly, a standardized satellite format. And this was the payload for a parabolic rocket flight. And so No Touch Robotics sort of started a bet with a space project here in Switzerland that we can manage to levitate a particle throughout all phases of flight, that meaning the launch, the zone where there is zero gravity, and then also up to the point where the parachute opens for slowing down the rockets on landing. And this actually worked. So the particle was stably levitated through all these phases. The forces were too low once then the rocket or the rest of the rocket hit the ground. And with this, I want to thank you very much for your attention, and I'm very much looking forward to your questions. Thank you.
Yeah, thank you very much, Marcel. It was very exciting, and sorry, I make a mistake in the questions, and now I see your questions in the right window. So you can. It's time to ask your questions to Marcel. Now you can tip in. So just a minute. Can machining be carried out during the gripping process?
That depends on what kind of machining it is, of course. What we have done in the past is, for example, built a clamping mechanism for laser milling.
Okay.
So that works, yeah.
Good. Wait a second. Good. Yeah, then thank you very much, Marcel, and let's give Marcel an applause here. So, yeah, and now very warm welcome to our third speaker, Nicolas Alt. He is CEO of Visevi Robotics. And yeah, Nicolas, please introduce yourself.
Yeah, thank you very much. Thank you for this invitation to Robolunch. Nice to meet you here again in this virtual environment. I just got a request for the screen sharing, so
now it should work. Yeah, perfect.
do you see my screen in full screen? Ah, yes,
Yeah.
I know you're the wrong one, I guess.
It's not in full screen, but
Yeah. Can I redo this again? And change somehow? No.
no, it fits perfect.
All right. Yeah, feeling by seeing, grasping by seeing, that's the topic of my presentation. I want to explain you in this presentation why smart robots are vision first. You see, robotics is also a spin-off from TU Munich in our case. We are based on 5 years of research as well, actually. And in our research, we asked the question, how can we improve the perception of smart robots for grasping with haptics and vision? So during this research, we really learned that what an intelligent robot really can do depends on what it can see and understand from the environment. We thought, doesn't the camera become the essential sensor of a robot? And can it not be used for many applications at the same time? I teamed up with Stefan to build such a robot from the hardware and software, and this is how we started with Sehen Robotics. There's a little bit of context here. An industrial robot is built with the concept of mechanics first in mind, with very precise gears, rigid structures. But now if you add making this intelligent, adding sensors, you end up with a pretty complex system, especially for the hardware. You need wiring in very small spaces, and you end up with high costs and high weight. A typical camera-driven robotics application is shown here. Bin picking with changing undefined objects, such as these vegetables here. Before the robot can do anything, we need to find the objects and grasp them at the right location using camera and computer vision. So what the camera really does here is detection of object, detection of grasping locations, scene understanding, which means where is the bin and so on. But we even go beyond that and we see robotics. And that's something we do with the concept of camera-based sensors. Camera-based sensors give you a sense of touch in the fingers, but without adding electronics and wiring to the fingers. Here you see a tactile signal of grasping this tomato, but I will explain this a bit more in depth in the following of my presentation. So why does the camera become the essential sensor? Well, it is used already nowadays for seeing and understanding the environment, but then it can also be used to simplify mechanics or retrofit existing mechanics, and it can replace other hardware sensors. The sensors you need on a smart robot arm are joint angle encoders to give you the position of the robot arm, force torque sensors in the wrist, and if it's about sensitive grasping, also more and more tactile sensors in the fingers. And these are actually the 3 main sensors you need for a sensitive robot arm. And that's what we can realize purely camera-based with computer vision. And in this slide, I want to explain a bit more about how this works. We have a camera on the robot which looks onto the gripper itself, pretty much like we humans do with our eyes when we grasp a cup or something. And this camera is connected to a computer vision software for image understanding. Now we employ a simple yet effective trick. We add passive markers onto the robot arm and the gripper and elastic elements. Passive means that there are no electronics in these elements, which makes them very low cost, lightweight, and mechanically simple. So exactly what you need to reduce the mechanical complexity. By looking what these elements do, how they deform with the computer vision software, we can realize a virtual software sensor that replaces numerous hardware sensors on a robot arm. Now we want to talk here in this presentation about grasping. So I want to show you this little application we did together with Dramatic about sorting transparent objects, glass and plastic objects, based on tactile signals. They are taken from the white tray and put into the red box. Here you see again how this tactile profile looks like. The tactile profile is the pressure along the fingers. When grasping this round glass object, you clearly see how this signal distributes. Now, in this instance, we grasp a soft plastic object, which actually deforms while we grasp it. That's something we can see with a tactile sense, and we can distinguish this plastic object from a hard glass object and sort it accordingly. This video goes on a bit, but I want to leave you with it here. I sent the link to our YouTube channel to the organizers. I hope they can maybe forward this to all of you. I also said we can simplify the hardware of robots. And this enables, in our future vision, novel applications of robots. For instance, think of drones that do delivery applications. They already have a camera pretty often for navigation, but they lack simple manipulative skills. So why not equip them with a lightweight, simple robotic arm to place items? Or in home use cases, a vacuum cleaner that can clean into corners and also pick up your left socks or toys could be very helpful, right? But in this case, we need a really simple robot arm, which may cost only around $20 to $30. And we can do that by using the existing cameras that those robots use nowadays for navigation purposes. In Industry 4.0, we can think about mass production for individualistic items, and telepresence for maintenance operations at home and in offices. With that, I would already like to conclude. As a startup, we are always looking for innovative pilot customers. We offer camera-based sensors for intelligent grasping. We have a bin picking software that we can combine with those sensors for flexible bin picking. And we offer development services in ROS and robot vision. You can contact me by email at n.alt@vcv.com, on our website, and via LinkedIn. With that, I would like to conclude and thank you for your time.
Yeah, thank you very much, Niklas. Very impressive solutions you shown us, and yeah, now the participants has the opportunity to ask some questions in the chat. There's one question. Since you mentioned Industry 4.0, how do you plan to contact the higher layer for automation pyramid, MES or ERP level?
So I didn't understand. How do I contact the higher level of warehouse automation? Or
yeah, right. How do you connect your gripping system with the higher layer of the other systems like an MES or ERP system? Do you have an interface, or do you use maybe OPC UA for this connection?
Yeah. So our philosophy is that we have our product with open interfaces, like even defined in an open source sense, to make it possible for any system to interface with us. Now, of course, how do we bridge into interfaces of existing systems is, in that case, we will need to establish the interfacing. We have not done that so far. So far, we have used other open interfaces or HTTP-based APIs to interface with our system. That is something, that's a software model that we would add the customer-specific development.
Mm-hmm. Good. Can slipping of the object be detected if the gripping force is not sufficient?
Yeah, that's exactly one of the strengths of tactile sensing. You can actually see when the object starts to slide out and even increase the gripping force to prevent it. or at least you can document this failure so you know that you haven't picked something.
Okay. And do you use several cameras for all these jobs, or is one camera enough?
One camera can be enough, even to cover the scene, the object, and the gripper with one camera. In that case, you would probably use a wide-angle lens and a high-resolution sensor. Our algorithms are flexible. They can work with one camera or several. That depends a bit on how your workspace and how your robot is built up.
Okay. If you integrate elasticity in the robot arm to measure force or torque, will this have disadvantages of the precision?
When you think about precision in service robotics, the standard of the industry is only about 1 centimeter. So we are far from anything we see in industrial robotics. The advantage with our system is that we always correct it online. So we are actually better than typical service robots. We allow deformation in the robot arm. Like that, you can even build a robot arm out of low-cost elements like plastic parts. And then we correct it online with a rate of around 100 hertz. So we can cope with that. Of course, at one point, you could get into shaking and vibrations. And that is the case when the elasticity is too high, the damping is too low, and the weights you carry are also too high. So this is a situation to avoid. So you need to have enough elasticity to avoid those vibration cases.
Good. Thank you very much, Nicolas. Yeah, let's give Nicolas an applause.
We have one more question here now. How do you deal with possible obstructions?
Okay.
And verify that what may occur. So an obstruction that something covers the view of the camera, of course, is a very common problem in vision. We say for safety considerations, you need to solve this anyway. You need to be able for a smart robot to see what the robot is doing. One approach is to use several cameras, which drastically reduces the chance of random occlusions. And then, of course, the occlusions are considered in our motion planning processes. So motion planning typically already avoids obstacles, goes around an obstacle, avoids hitting the table. And in addition, we have a constraint in our motion planning that we want to keep the view on the fingers on the gripper.
Okay, good. Yeah, thank you very much for your presentations to all speakers. And yeah, this was our second edition of the VDMA Robolunch, and I hope you enjoy it. And we will continue the series soon, and we'll keep you informed. And we have a survey here. One moment, I switch my screen. Now I hope you can see it. Yeah. So yeah, please let us know how you liked it and leave us some comments so we can continuously improve, and simply scan this QR code here. Yeah, thank you and see you soon at Robolunch number 3. Wish you all Merry Christmas and a Happy New Year. Stay healthy. Thank you very much. Bye.